Here we are back again. It looks like I haven't copied over the example code yet. Let me go ahead and do that very quickly. All right, so okay, so that needs to go over chapter 2 and 23. Okay. All right, so I've copied that over now. Okay. I guess I did not put over the lecture examples folder, but it should be uploading now, and so it should be available shortly. All right, so this is our final week. So what we will plan to do today is I'm going to finish up the efficient algorithms discussion. Then I would like to introduce the sorting discussion. I won't be able to get through all of that. There's just too much in there, but I do want to just kind of introduce that concept of why sorting is important and how there are some different ways to do that. And then finally, what I'd like to use our final time together today for is to go over the final exam and kind of talk through some of what you can expect to do from that, what you can expect from the final exam that will be in a couple weeks. All right. Okay, so let's get right on into it with the continuing on with the efficient algorithms. I'm going to pull those slides up as soon as they come on.
Sir?
Yep.
Will we have a quiz about assignment 4?
No, there's no quiz on assignment 4. There was that was intentionally left out of the assignment description because there would not be enough time to have those quizzes graded and returned before the final grades are due.
Thank you, sir.
Sure. All right. There we go. Okay. So this is where we left off. Was the big O of this algorithm is now the reason why this if statement, we call this big O of n, is because in order to determine if the list, and if we imagine this is some kind of list like array list or linked list or something like that, the way to determine if that list contains a certain value is we assuming that that list is not sorted, and we'll talk about in the search algorithm here in a moment. We'll talk about the binary search, which we introduced last semester. But assuming it's not sorted and we just need to go through the whole thing and possibly to see if the value is in there or not, it could be in the worst case we may have to search through the entire list. All right, so we call this big O of n because we don't know, the compiler, the executor, it can't know if this list contains sorted values or not. All right, so because it doesn't know that, it has to just go through each item until it either finds this value or it has to exit without finding this value. So that's why this is big O of n. Normally, I would say that doesn't mean that every if statement is going to be a big O of n. An if with just a normal condition, like if x is less than 5, for example, would not be big O of n. If x is less than 5 would be big O of 1. It's something that's done in constant time. It always takes the same amount of time to test whether x is less than 5 or not, right? And whereas here, to go through the entire list, based on the size of the list, which that's what n represents. N represents the size of the list. And so based on the size of the list determines how long it takes to execute this if statement. Okay, so that's why this is big O of n. So that's going to take up big O of n time to test it. Then what's inside of the if statement is constant time. Doesn't matter how big the list is, we can print out element E in constant time. Right. The other side of that if statement, we're going to go through each object in the list and print it out. This is not constant time. This does depend on the size of the list. And so now if the size of the list is n, which is very common, by the way, very common that we refer to the number of items in a collection, in a list, in an array, in a set, whatever. We refer to that as n. Hopefully you know that from your math classes as well. All right. So this will take n executions, right? So if n is the size of the list, this is going to be executed n times. So the complexity, as we ended on our last lecture talking about, was that it is the test time plus whatever the worst case. So the positive side of the if statement, the true side of the if statement, is a constant time thing, as a big O of 1. The false side of the if statement is big O of n, because it depends on the size of the list. It's directly proportional to the size of the list. And so that becomes big O of n. So the if statement, big O of n, plus the else side of this, big O of n, means total big O of n. Okay, which basically, again, it does not mean that it doesn't mean that this if statement takes the exact same amount of time to execute as this whole else for loop. We're not saying that it takes the exact amount of time, but what we're saying is that this whole algorithm is proportional. The amount of runtime is going to be proportional to whatever the size of the list is. That if this list is size 10, then it will, let me say it this way. If the size is some value k, we'll say k, then if we were to increase the size of the list 10 times to make it a size of 10k, then what would most likely happen is that algorithm would run somewhere in the neighborhood of 10 times the 10k. Yes, it would take 10 times. I'm making sure I'm saying this right. Yeah, it would take approximately 10 times the amount of time. Okay. All right. Now, the most ideal algorithm we can get to for anything is if we can ever get to something what we refer to as constant time. Meaning, in constant time, it does not matter how big the input size is. If the time of the execution is not at all related to the input size, we can put in an array of 100 items. We could put in an array of 1,000 items. We could put in an array of 1,000,000 items, and it's going to take the same amount of time to execute our algorithm. Then that would be what we call a constant time algorithm. So, like as an example in this previous slide, I called this line here, this system.out.print line, I called that a constant time, big O of 1, meaning it does not matter what the size of the list is. The size of the list has no bearing. The size of the list has no impact at all on how long this line will take to execute. Okay. So if we could ever get to a constant time search algorithm, if we could ever get to a constant time sorting algorithm, those would be great. And you could probably become a very wealthy person if you could ever find a constant time searching algorithm. Google would definitely love to hire you if you could find a constant time searching algorithm. And that's because basically searching a whole collection of things, a set, a list or whatever, it takes time to figure out to find the value you're looking for, right? And because you're going to have to search through multiple elements in the array or the set or whatever before you have found your item or until you know for sure that it's not there. Okay. All right. There's a search animation. I encourage you to look at some of there's animations available on like Wikipedia and stuff like that. I encourage you to look into these to see how these searching algorithms work. So here in this example, they talk about the linear search. Let's say what we were looking for was, let's say it's the value 9 is what they show in their example here. With linear search, we can just basically start in the first value, and if that's not what we're looking for, we move to the second and the third and the fourth until we finally either get to our value, like here, or we go through the entire array, we go through the entire data the entire collection, right? And we have not found the item, and we exit. Okay, that's how linear search works. Binary search we talked about last semester as well. We talked about linear search and binary search last semester a little bit. And binary search, it depends on having an array or a list that is already in sorted order. Okay, and because it's in sorted order, like a dictionary or like a phone book, if you guys remember phone books, all right, that's a long time ago we had phone books, right? The idea was that you wouldn't necessarily start on the first page and look for your item and then to the second and then to the third. What you would do is, because you knew that this collection was sorted, that therefore you could start right in the middle, and if your value was not there, you could remove half of the items that you wouldn't need to look in those. So let's say we're looking for value 6. We start here right in the middle on 10. We know that it's not 10. We also know that 6 is less than 10. So therefore, we don't have to look through any of these, right? So we can just say, get rid of all those. We don't want to look in those anymore. So what we're going to do instead, we're going to look only in this set. And we're going to do this again. We'll start in the middle. Okay. It's not 5. It's greater than 5. We don't need to look through any of these. We only need to look through this set over here, through this set of values over here. Now, binary search runs in what we call logarithmic time. Okay, what that means is because we don't have to search every value in the array or in the collection in order to find our value, it's much less. Okay, and by the way, in computer programming, anytime you see something referred to as log n or n log n, we'll talk about there's sorting algorithms that are n log n. Anytime you see log n, that is log to the base 2. Okay, and that's not log to the base 10. It's not log to the base e. Those are your math terms. In computer programming, because we deal in binary, it's log to the base 2, and there's all kinds of fun ways that we understand that. And this is how we would look at it, is that because the time to search through n items for binary search is equal to the time to search through n over 2 items plus some constant value. So basically the test of does it equal that, right? And basically, it's a lot of math stuff, and you'll learn more about this in your algorithm courses and your data structures courses. But basically, we can use this fact that the time to search through n items is basically the time to search through n over 2 plus some constant, which is the time to search n over 4 plus constant twice over. And what we end up with is n over 2 to the k. If we assume n is some 2 to the k value, right, then this would be the time of searching 1, which hopefully we understand that's a constant value. Time of 1 is a constant value, plus c times k. Well, what's k? If we solve for k from this formula, n equals 2 to the k, we get k is log n. Okay, and that's why this algorithm, we consider it to be log n. And if we were in the classroom, I could sit here on the whiteboard and really go to town with this, and really, sorry, that's an idiom. If we were in the classroom, I could get up on the whiteboard right now and really kind of write this out and help you understand why this is what it is. And for anyone who's interested, we can talk about it further. But it is pretty interesting the way this works out. Now, one of the things about binary search, though, as opposed to linear search, is that it's a trade-off. So in order to have the binary search have that much faster searching capability, it means that something must be true of our collection to start with. It must be sorted in order for us to use binary search. If we don't have a sorted collection, then if we have a mixed collection, a mixed array, then we can't use binary search on it, right? And so we have to start with and maintain a sorted array to start with before we can even use binary search. Okay, and so there is a trade-off here because the array initially might not be sorted, so we're going to have to do the work to sort it before we can search it. Okay, but if we have an array that is sorted to start with, and anytime we add new items into it or delete items from it, if we maintain that sorting in there, then we can use binary search to be able to search through things very quickly. All right. We talked about logarithmic time. This selection sort. So I did say we were going to talk a little bit about sorting. What I'll probably do is I may just I'm going to skip over this part because I think this is part of the sorting discussion, so I don't necessarily want to go through it here. Okay. Now, but I do want to talk about quadratic time because the selection sort, as we'll see when we look through those slides, is what we call quadratic time. It's n squared. It's an n squared algorithm. And the reason why that's important, the way we can understand that is that we must visit in the selection sort, we must visit through the entire array once to find the highest value and put it into place, or the lowest value, depending on which side we're going to, right? And then we must do that again with the remaining values, the n-1 values. Okay, and so when we do that, we have to do that n times. So we go through n, some calculation involving n elements in the array, and we go through it and do that n times. So that's why it comes out to be about n squared. Okay, it ends up being somewhere like in that remember that n squared plus n divided by 2, that kind of thing. That's where it ends up kind of actually being. And if we're talking about actual calculated runtime, but as we talked about last time a week ago, that n squared plus n divided by 2, big O is n squared. All right. Now, what this means is that for a quadratic time algorithm, for an n squared algorithm, is that if we were to have some list of size k, for example, and then we were to use the same algorithm with a list of size 10k, no longer will it take 10 times the amount of time to run on the larger set. Instead, it will take 100 times the amount of time, right? Because that's n squared, because k, a size k versus a size 10k will now take n squared amount of time, right? So so if it was k squared for the k size set, 10K is going to be 100K squared, right? So it's going to take 100 times the amount of time, right? It's a lot slower. All right. This is how we would analyze that. Insertion sort is another example of an n squared algorithm. Okay. All right. So we talked last semester, we talked about the towers of Hanoi for recursive programming, right, where we move the first n-1 disks, we move some disk from A to B, and we move the n-1 disks from C to B. And that was, we use this as an example of how to do a recursive algorithm. Now, to calculate its runtime, well, what is the time to move in disks? And we actually showed this, if you guys remember, there was this whole, we did this chart kind of in disks, how many total moves did I need to make, right? Hopefully you guys remember that, where I talked about for one disk, how many moves? Oh, there's one, that's easy. For two disks, 1, 2, 3, right? And what we discovered was that it was what, that n squared plus n divided by 2. Is that right? No. Sorry. How many moves did it take? Trying to remember. Man, that was a long time ago, guys. This pandemic has got my brain not working well sometimes. All right. But was it n squared? No. It was 2 to the n. It was 2 to the n minus 1. That's what it was. 2 to the n minus 1. Yeah. All right. Yeah, that's right. Videos are still on YouTube. Maybe we can go watch them at some point. All right. But the point is that now we can do that through more of a calculated function type of writing. Okay. Where instead of having to go through example by example, how many moves for one disk, how many moves for two disks, how many moves for three disks. Now what we can say is, well, the time to do n disks is going to be whatever the time to move n-1 disks is, plus the constant value of moving the one disk, plus, again, moving those n-1 disks again. So 2 times the time to move n-1 disks plus some constant value. Well, if we then expand that out to n-2, involving n-2, and so forth, what we end up with is we will end up with this some constant value times 2 to the n minus 1, which is what I was talking about. We did that through how many moves did it take, and we did that through a chart value. Now we're showing how to do that through an equation. All right. Well, this becomes, okay, 2c times 2 to the n minus c. If we do the distributive property here, this non-dominating term, we just cancel it out. We ignore the multiplicative constant, and we end up with some 2 to the n, right? Big O of 2 to the n. And remember, we even talked about the whole legend of the Towers of Hanoi and how many seconds, if our monks were able to move one disk per second, how long would it take them to move the 64 disks, right? It's like we're still very far away from the end of the world, right? Although I'm sure many people have probably thought, well, hell, with this pandemic, maybe we were closer than we thought. Right, that kind of thing. But the idea here is, okay, so now if we have some set of n disks k, right, well, it's going to be based on 2 to the k is how long it will take to run the algorithm. Well, if we increase that size k to 10k, it's no longer 10 times the amount of time. It's not 100 times the amount of time. It's 2 to the 10th times the amount of time, right? Okay, which means it's going to expand really quickly, because does anyone know what 2 to the 10th is? Off the top of your head. I'd be surprised. Some of you may know it if you're not a first-year student, right? Well, 2 to the 10th is around 1,000. It's very close to 1,000. Okay. So now that takes a much bigger data set, right? It grows really, really fast. Okay. So here's some common what's called recurrence relations and kind of how the big O stuff works. Is so your general searching, your binary search algorithm is going to be running in around log n. Most of your search algorithms, your linear search, I guess actually, well, linear search is the only one. I think generally sorting algorithms are going to be around n squared. Right? Generally, sorting algorithms are going to be around n squared. Merge sort, and another one that you'll learn about in your algorithms class is called quick sort. Those are in log n, which, again, it may not seem like that's a big change, but it can be huge when we start talking about really, really large sets of data, and we need to sort or search those things. It can make a huge difference. Okay. The towers of Hanoi we just talked about was 2 to the n, and we talked about the recursive Fibonacci and why that was not efficient was 2 to the n also. All right, so if we compare these growth functions, right, constant time is going to be our fastest, logarithmic next, linear, big O of n, what's called log linear, n log n. This is your quick sort, your merge sort, your faster sorting algorithms. N squared is greater than that, n cubed, and then n to any other exponent. So n to the 4th is going to be greater than n cubed, n to the 5th is going to be greater than n to the 4th, and so forth. And then finally, the largest algorithms that really you'll ever deal with will be around the 2 to the n time. Okay. Now, the thing is, what some of you may be saying to yourselves, wait a second, because what if n was 0? If n is 0, then this is small. This and this and this and this are all the same, and they're all smaller than this. Right? So if we look at it in terms of a graph, right, is here you've got, wait a second, this big O of 1, all of these algorithms down here, all of these growth functions here are all smaller than this one. So how can you say that big O of 1 is automatically better than these other ones? When look, they start out way down here. What if the size of our data was 1? What if the size of our data was 2, like this algorithm here? This is the log n, right? Okay, what if the size of our data was 2? Then the log n algorithm would be faster than the constant algorithm. And that's true, but I'm sure you know by now that there's very few data sets of size 2, right, or 3, right? Most of the amount of data that we deal with is much larger than that, right? Much larger sets of things that we put together. Yeah. And so what we're really concerned about is how fast does this function grow, right, as the data set gets bigger and bigger and bigger. Okay. And as you can see, yeah, that maybe let's take the n squared one, for example. N squared starts out way down over here, right? But as n gets bigger and bigger and bigger, it starts to grow really fast and what we call exponentially. Right? And so if we had an n squared algorithm, that would be, it would get much slower and take much more time as that data size of the set of data got bigger and bigger. Okay. All right. We talked about last semester, we talked about Fibonacci numbers, and that it might seem like Fibonacci would make a really good case for being a recursive function, But the problem is that what we discovered, actually there's no slide on it here, the slides are from last semester. What we discovered was that basically if we do it as a recursive definition, it gets to be really a slow algorithm, and it's because we're calculating the same thing multiple times. So let's say we were looking for index 10. We're looking for the 10th Fibonacci number. Or in this case, I guess that's the 11th technically, but index 10. All right. Well, then we've got to calculate whatever Fibonacci is at index 9 plus whatever it is at index 8. And then we got to add those two together. But if we do the same thing again, calculating what's index 8 and index 7, add those two together to get what's at index 9, well, but we calculated index 8 already to add it to the 9 to get to the 10th one, right? So why should we calculate index 8 to get index 9 if we needed it before, right? So if we do it as a recursive definition, what ends up happening is we end up calculating these lower indexes many times when we don't need to. All right. So what we could do instead, we talked about this, is we could calculate these earlier values and add them together until we get to the one that we want, and then just return it. Okay. This new algorithm, instead of being 2 to the n, ends up being big O of n, much faster. Okay, if you remember correctly, if you remember back here in this, 2 to the n does this thing here. Big O of n is this one over here. Okay, this is very slow. It takes this is the number. This is the amount of time it would take this side of the graph here. So 2 to the n takes a lot of time. Big O of n, not a lot of time, right? So much better solution here. And what we refer to this as is what's called dynamic programming. And the idea is that, yeah, Fibonacci seems like it might be simple and easy to program as a recursive definition, but it can end up being something that's a very slow algorithm, right? But it's inefficient to use recursion, and because of the subproblems that overlap. The idea behind dynamic programming is we solve those subproblems, like what's the thing at index 8, we store that result, and then we use it later to solve the problem of what's at index 9, for example. Okay. And that way we don't redundantly compute the same thing over and over again. Okay. Let me see if there's anything else specifically I wanted to go over here. There's an example of this greatest common denominator that you can look at. That's a pretty interesting study there. Finding prime numbers. There's some examples in the code examples here. Basically, some 3 different versions of finding prime numbers. One is by trying to just brute force it, right? Let's say that we want to find all the prime numbers up to n, right? Up to yeah, that's right, up to n. Right. Well, we could just say, is 1 a prime number? Divided by everything less than 1. Well, yeah. Is 2 a prime number? Divided by everything less than 2. Is 3 a prime number? Divided by everything less than 3. Is 4 a prime number? Divided by everything less than 4. So forth. And that could take a long time, right? So if I wanted to say, okay, is 137 a prime number? Divide by 2. Is there a remainder? Yes, it's not. Okay, divide by 3, divide by 4, divide by 5, divide by 6. But what you'll notice is there is, well, here's a problem, right? If 137 was divisible by 2, I don't need to check, or sorry, if it wasn't divisible by 2, I don't need to check if it's divisible by 4 or 6 or 8 or 10, right? Because if it was divisible by any of those, by 4, 6, 8, or 10, it would have already been divisible by 2, right? And so we can use that kind of some knowledge about how of what we're searching for, in this case the prime numbers. We can use some knowledge about those things to come up with a much more efficient way of solving that problem. Okay. Again, those are some examples that are in the code examples, and I definitely encourage you, if you're interested in that, to look into those. And I am going to talk about this a little bit more, this idea of what can we know and what can we understand when we talk about the final exam review, because there's some special stuff that's coming up in that today. All right, let me check and see. Let me see if there's anything specifically more that I wanted to go over in this set of slides. Okay, one final thing here, is so the big O notation, right? Again, I want to repeat this. It's not a this is how long the algorithm is going to take. Oh, it's big O of n, so therefore it's data size of 100 is going to take 100 seconds. Like, it's not that we're not saying that. What we're saying is that it is an idea of how efficient and how much the size of the data is going to impact the runtime of the algorithm. Okay, so you could have two solutions that are both big O of n, and one of them takes less time than the other pretty much always. Okay, so we are not necessarily trying to come up with an exact, this is exactly how efficient this algorithm is. We're coming up with an idea of how to understand how size of the data, number of items in our data set is going to impact the runtime and affect the runtime of an algorithm. Okay. All right. I would say make sure you understand 31. Okay. This, right? Make sure you understand how these different algorithms, growth functions are related to each other. Which ones are greater, which ones are less, and that kind of thing. Okay. Again, this class is not your algorithms class. That's coming up later for you guys. So I'm not going to ask you in any type of like quiz or exam for you to be able to do something like this, where you calculate t of n equals this, and that therefore it's n log n. Okay, that's not this class. That's a future class for you. But I do want you to know at least how these different growth functions are related to each other. If I were to say, where does big O of n squared log n fall? Okay, well, hopefully you would be able to tell me that n squared log n would be greater than n squared, but less than n cubed. Okay, so n squared log n would fall right in here. Okay, all right. I hope that's clear. What we'll do is, I feel like we've gone over quite a bit here in this first hour, so we'll take our break now, and then we'll pick up with the sorting lecture slides when we come back from the break. Okay, so I'll see you in 10 minutes.